Hi, William. Can you hear me okay?
Yeah.
I see that the camera's still not working correctly on your side.
Yeah. I don't see any way to plug it in, unfortunately. I mean, it seems to be plugged in, so I don't know why it's not working.
Oh, no, that's fine. I just want to make sure you can see and hear me okay.
Yeah.
Great. All right, let's get started then. So hello, good morning, everybody. I hope you guys had a nice break. I sent out an email yesterday sort of summarizing the last things that we have to get through this semester to complete our work in this course. So in that email, there's information about the optional final, as well as how to approximate your grade at this point in time, anything like that. So make sure you read that. And if you have any questions, definitely let me know. There's going to be a review on Thursday of this week and Monday of next week that William is going to do on the Chapter 5 review that's posted in Moodle. So if you are interested in that, make sure you stop by. I will send out a reminder about that tomorrow. Otherwise, we are just continuing through our Chapter 5 work, and we will just sort of go from here. So just as sort of a reminder, we have to do sort of the last subsection of 5.1, which we didn't get to last time. And then that ties into the beginning of the next section. And it's a little wonky since we had the break in between, but hopefully you remember enough of what we did last time that it's not too much of a stretch. The beginning part is a bit conceptual, and I'll probably talk for a bit longer than I usually talk in the beginning, but we will get to practice problems and things of that sort. And today we will be using calculators. So if you do have your calculator with you, you'll be using that. And if you don't, you can certainly use your cell phone to go on websites like Wolfram Alpha or something like that to do some of the computations that we will look at. Okay, so I'm going to go ahead and switch over to the DocCam. And I'm going to turn off my own video just because I think it helps the bandwidth. And then we'll get going. Okay. So just as a reminder of what we were doing last time we were talking about approximating the area under a curve. And so the way that we approach this, remember that curve was a rate. And what we did is we fit in these little rectangles to try to get an approximation of how much area there was. And so we talked about a left-hand estimation and a right-hand estimation. We said the bigger value was an overestimate and the smaller value was an underestimate. And within that, we sort of had a couple of key variables that we used for different definitions. So just as a reminder, we had A and B, which were our endpoints. We had N, which is the number of rectangles. And we had delta T, which was the value which we were counting by, which was also the width of one rectangle. Right, so oftentimes you're counting by 2s or by 4. So if delta T is 4, that means you're counting by 4s to get from A to B between the endpoints. We also had this relationship that delta T could be found by doing B minus A over N. So these are all related. And one of the last things we did is we learned that if delta T is smaller, N is bigger, right? So if we shorten the width of a rectangle, we have more rectangles we can fit in, and it was a better approximation. Okay, so that's sort of a summary of what we need to remember from last time to sort of get into what we will talk about right now, which is Riemann sums. So all the problems that we looked at in the last class, we considered very sort of specific and bounded problems. And now we want to look at how we might do that in a more generalized way. And so the way that we're going to approach this is by considering a generic function, f of t. And we're going to consider how we might write this in a generic way to represent a left and a right-hand sum where we can fit in as many rectangles as we want between our endpoints A and B. Okay, so A is our left-hand endpoint, B is our right-hand endpoint, f of t is a generic function, and then we're going to do both a left and a right-hand representation, okay? So we're going to talk about this picture and what the different parts mean and how we're going to label them. And then we're going to talk about how we can write some things in a more general form. So remember, if we're doing a left-hand approximation, the left-hand corner of each rectangle is what touches our function. And why that's important is because, again, when we find the area of each rectangle, we're doing width times height. And the width of each one, we can call delta t, right? That's what we're counting by. So if delta t is 1, that means we're counting by 1s. If delta t is 3, that means we're counting by 3s, so on and so forth. And so that allows us to generalize this for any delta t. So the width of every single rectangle is delta t. Now the height is where things get a little more complicated. So on a left-hand approximation, the height of the first rectangle we find by plugging in the value from the left-hand corner between these two values into our generic f of t function. So if we're going to be plugging things in, we need a way to talk about these points that are not just integers, right? Because we want to be able to count by anything. And so what we do is we create an index where the first point is t sub 0, the next one is t sub 1, then we'd have t sub 2, ... And then the last one would be t sub n, okay? So even though in this picture, n equals 4, there's 4 rectangles, we are trying to make a generic situation where we can put in as many rectangles as we want between A and B. So maybe we want 8, right? So they're only half as wide and we fit 8 of them in here. Maybe we want 16, right? So we call this t sub n to recognize that we can fit as many rectangles as we want. Okay, same index over here. The first point, t sub 0, t sub 1, t sub 2, all the way up to t sub n. Okay, so how do we write this a little more generically? Well, let's start with the left-hand sum. Okay, so let's just focus on this first rectangle. And so the area of this rectangle is width times height. The width of every rectangle is delta t times the height. So the height is the y value we get when we plug in the left-hand point between t sub 0 and t sub 1. We pick the one on the left because we're doing a left-hand approximation. So between t sub 0 and t sub 1, we're using t sub 0 to get the height of this rectangle. So what does that mean? We're using t sub 0. Whatever that value is, that's an independent value. We plug it into our generic function, f of t, to get the corresponding y value. So that y value we can write as f of t sub 0. So if we had a value for t sub 0, we would plug it into whatever the function is, and that would give us the y value, which is the corresponding height. Okay, so that is how we represent the area of the very first rectangle in a left-hand sum. Similarly, if we wanted to do the area of the second rectangle, the width is still delta t, that's the same. And now the height of the second rectangle, we look at the two subscripts, t sub 1 and t sub 2. We pick the one on the left, t sub 1, to get the height because it's a left-hand approximation. So the height we get from plugging that into f of t. So we get delta t times f of t sub 1. Okay. Now remember, we want to be able to put in as many rectangles as we want. So we do plus, dot, 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 plus. And now we're going to jump to the last rectangle. And this one's a little goofy, right? It's a little bit different. We're using an n here, even though, again, visually you see 4, but we want to be able to account by having more if we wanted to. So the width will still be delta t. And then the height is this point right here. So since we want to be able to vary n, that means that this point is also going to vary, right? It depends on what n is. If n is 10, then this is t sub 9. If n is 100, this is t sub 99. So the way we write that last point is f of t sub n minus 1, the one before n, right? That's going to give us the height of this last rectangle here, which we'll call rectangle n. So this is how we write a generalized form of a left-hand sum, a left-hand approximation. If we were to do the same thing with the right-hand approximation, how would it be different, right? So let's do the same thing. So let's look at the first rectangle. The first rectangle is going to have a width of delta t, but now the height, instead of picking the left-hand point between the two, we're going to pick the right-hand point because it's a right-hand approximation. So the height of that first rectangle is f of t sub 1. And then for our second rectangle, again, delta t, but now the height is going to be f of t sub 2 plus dot, 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 plus. And then the last one will be delta t times f of t sub n, because we're picking the one on the right. And so for the last one, we're picking that t sub n. So the difference between the left and the right-hand sum is where we start with this y value, t sub 0, t sub 1, and where we end, t sub n minus 1 and t sub n. And that makes sense because with a left-hand approximation, we don't use the rightmost point, t sub n, right? So we use n minus 1. And with a right-hand approximation, we don't use the leftmost point, which is the t sub 0. So in sort of a short way, this is a perfectly appropriate way to represent the left and the right-hand sum. However, I want you to imagine that we wanted to write out a sum with 100 rectangles, okay? It would take a long time to write out all of the terms for 100 rectangles because we'd have to write out a term for each and every one. So in math, we have a symbol that represents what's called summation notation. You may have seen this before or you may not have. And this symbol is what we use when we're going to add up a lot of terms that are similar, okay? And what it does is it says, okay, what's the similar structure for each term? So we can just write it as one term instead of all the terms listed out. So what does that look like? So for a left-hand sum, delta t is the same in every single term. F is the same. What's different is this subscript, okay? And we call that an index. So we write an I there, and then we have to tell the summation the values where I starts and I finishes. So I starts at 0, and it goes until it gets to n minus 1. So what this does is it says delta t f of t sub 0 plus delta t f of t sub 1 plus delta t f of t sub 2 plus delta t plus f of t sub 3 plus, and it keeps going until it gets to n minus 1. And in a given problem, that would be a defined number. So if you wanted 100 rectangles, that would go until 99. That's what that represents. That's called summation notation. And when you use it in this context for area under a curve, it's called the Riemann sum. So the left-hand sum looks like this. And the right-hand sum, delta t, f of t sub I, the difference is in the index, right? Because for the right hand, we said we started at 1 and we went until n. So when we look at these two, the main difference, again, is this index, where we start, where we stop, okay? Now, we have to go back to this point here. I'm going to scroll up for a second. If delta t is smaller, n is bigger, and that gives us a better approximation, okay? So remember, we would do a left-hand sum and a right-hand sum, and we said that the exact area under the curve has to be between the overestimate and the underestimate, right? So if we did it and we found one to be 10 and one to be 30, we knew that the exact area had to be between 10 and 30. Now, if n is bigger, it makes the approximation better. So if we can put in more rectangles, then our endpoints where our total area has to live sort of shortens, so we have a better approximation. So what we do is we tie in this idea back from chapter 2. If we let n get big enough, if we let n go to infinity, we're smashing in more and more rectangles. What will happen is that eventually the left-hand sum will equal the right-hand sum, right? So the overestimate will come down, the underestimate will come up. Oops, this should be a 1. And when that happens, right, your bounds are the same. This is a 1. So if I tell you that the exact area has to be between 5 and 5, it has to be 5, right? When they're the same, it gives you this exact area under the curve. So when these are equal, when you put in enough rectangles, you get the exact area under the curve. Okay, and it turns out that when we have the exact area under the curve, we have special notation for that. We move from an approximation to an exact area. Okay, so this is where we make the jump. So this is where we would normally end 5.1. We say, oh, okay, we have this exact area under the curve. And so now we jump ahead and we say, okay, now that we know this exact area under the curve, how do we talk about the notation and what it means? So this is just a summary of what we just said. This is a summation notation, right? Considering what's happening there. And so that's wrong. We'll talk about that later. So what happens is when we take this limit as n goes to infinity, and these end up being the same, we get new notation, which is called the definite integral. Okay, so let's talk about what these pieces mean, what it tells us, and how it's different than what we were talking about before. So notice that this S is sort of smooth, whereas the notation over here was like an E, okay? A and B are still your endpoints, okay? So where are we looking under the curve? These are your endpoints. Okay, so we have some function, f of t. We want to know the area under the curve between A and B, where we start, where we finish. Okay, now f of t is your function, which we know is some sort of rate, right? So remember, we've been looking underneath a rate function to tell us how much the original function changes. Okay, now here's where things get a little complicated. These two pieces, the dt and the integrand, okay, these are operators. What does that mean? So another operator that we know and we're comfortable with is the plus symbol, right? If I said, what is 3 plus 4? And you said 7. The plus is an operator that tells you what to do. It says add these two things together, right? Subtraction is an operator. It tells you to subtract things. In this scenario, what do these operators tell us? The first operator, these are bookends and they have to go together. The first one tells you to find the area under the curve. Right? That's what we've been trying to approximate. But now we're finding it exactly. So we're finding the area under the curve. And then we use the terminology with respect to, and then I'm going to put a line here. So the dt is an operator that tells us what variable we are looking at. Now, this is going to seem a little silly because we are always going to be using a single variable. So when we have a function in terms of t, this is dt. If we have a function in terms of x, this is dx. If we have a function in terms of q, this is dq. And the reason we need to have this is because if you go on to take more calculus, you'll learn that we have some functions that are called multivariable functions. So they have more than one variable. So you can have a function that has a t and an x in it. And if you want to talk about area under the curve, you need to talk about which variable you are considering. So we start this convention in single variable calculus where it always matches because we want to be able to expand on it later. So what does that mean? These two operators are going to disappear once you have found the area under the curve, right? Just like here, the 3 and the 4 and the plus are all gone because we found what happens when you use this operator. Same thing happens here. Once we find the area under the curve, it just equals some number, and all of these parts disappear because they were operators. Okay, so the definite integral is going to tell us the area under a curve between 2 points. Okay, so we did this particular problem last time as an approximation. If t is in hours of a 20-hour period, the rate at which the bacteria population is growing is given by f of t equals 3 plus 0.1 t squared. So last time when we did this, we did an approximation with delta t equals 4, and we found the area had to be between 252 and 412 bacteria. That was our upper and lower bound. But now we know that the definite integral will give us the exact area under the curve. Okay, this should be 327. But how do we get that number, right? We know that this symbology will give us the answer we want, but we don't actually know how to find it yet, right? And so it turns out that when we start this idea of area under the curve, we are going to start by doing this on a calculator, because what the calculator will do, or the computer will do, is it will fit in these rectangles, as many as it can, until the overestimate and underestimate are the same. If we do that by hand, that would be really complicated and it would take us a long time, right? We don't want to put in n equals 1 million rectangles. The calculator will do that behind the scenes. So I'm going to show you on my calculator the syntax that I use to plug this in. Depending on which calculator you have, or if you're using a computer, your syntax might need to be adjusted a little bit. Okay, so how do I enter this function in? Let me move this up here. So I have a TI-84. This will also be true for other versions of 84 or 89s. I start by going to the math button. This will also be true on an 83. For most of the TIs, you start by going to the math button. Then I need to go down to option number 9. So I have to scroll down, and it says FNINT. That means function integrate. So that's the first 2 steps for pretty much anyone who is using a TI. What's different is when I hit enter, it may look different than what you see on your screen. You will either see something like this where you can fill in boxes, or you will see on your screen FNINT. And I'll talk about how to fill this in a second. If you see boxes like this, that's when we're going to go ahead. So we're going to start by plugging in our bounds. So we have 0 and 20. So 0, then we hit up, move 20, and then I hit over. Then I'm going to plug in my function. This is a little funny. So I have 3 plus 0.1. Now, instead of t squared, I'm going to use x because it's easier for me to enter x everywhere. And it's the same function whether you use x or t. So this is the variable button up here next to alpha. So I'm going to do x, and then I'm going to hit the squared button, x squared. Then I have to go over, and I have to, again, fill in x to tell it what the variable is, okay? If your screen says FNINT, you are going to enter your function first. So 3 plus 0.1, you're going to use x squared, then a comma, which is above the 7, then an x, then the lower bound, comma, and then the upper bound. Okay, so yours is going to look like that. If your screen said FNINT, then you hit enter, and it will spit out the exact area under the curve. So it's 326.6, which is 327 if you round to the nearest bacteria. And that is an exact area under the curve. Okay, that's telling us exactly the area. And again, before we said we had to be between 252 and 412. So the exact area does fall between the bounds we had found before, but this is more accurate. Okay, so what I want you to do is I want you to try to plug one more in just so you can get comfortable with whatever syntax you're using here. So I'm going to give you about a minute and a half. I want you to try to plug in, this is x squared plus 3x plus 1 from 0 to 3. So again, if you have a calculator, see if you can figure it out on there. If you're using a phone or a computer, you can try things like Wolfram Alpha is a good website for computing. I think Desmos might do area under the curve, but see if you can figure out how to find that area. So take about a minute and a half, and then I will tell you what I got. Okay, take about 30 more seconds. Okay, so I'm going to show you again, just sort of the syntax that I used on my calculator. Here, I'll put it here for a second so we can get out of the light. So again, 0 and 3 are the bounds, x squared plus 3x plus 1 is our function, and then we need the dx. Once you have everything plugged in, you're going to hit enter. If you get an error when you hit enter, it's likely that you put a parenthesis in a weird place, and you may have to go back and fix it. When I hit enter, I get 25.5. So the exact area under the curve here is 25.5. Okay, so now we have sort of two diverging roads of what happens with definite integrals. Okay, so sometimes we're just plugging in functions. We're plugging in definite integrals. We're figuring out what the bounds are. We're putting them in a calculator or computer, and we're spitting out a number. But sometimes we are still approximating even though we see a definite integral in the setup. And we have to use context clues as well as read problems closely to recognize that we're not actually plugging anything into the calculator. So we're gonna do 2 quick examples of that to see how that might come up so that you don't sort of get swayed in the wrong direction. So for example 2, it says for a function f of t, or values for a function f of t are given in the table below. Estimate the area under the curve from 10 to 20 of f of t dt. So you need to think about what that means, what we know how to do from last time, how we would approach that on a table, and what some of the right answers might be. There's more than one way you can estimate. For example 3, we're given a graph and we're told to use n equals 1, so one rectangle, to determine bounds for the area under the curve from 1 to 3 f of t dt. What that means, bounds, is an overestimate and an underestimate to figure out where the exact area under the curve is bounded. Okay, so I'm going to give you 3 minutes. I want you to think about these 2 problems and try to think back to what we were doing last time and how we can apply that here. Okay, so we'll go over it together in about 3 minutes. Okay, take about 30 more seconds. So let's take a look at these and make sure we can understand that even though there's an integral in the setup, we're not actually plugging anything into our calculator or computer for these examples. So the first thing I want you to notice in example 2 is that we're interested in what's happening between 10 and 20. So we're not considering the whole table. We only want to know what's happening from 10 to 20. Okay. So then I also want you to notice the word estimate. So we know that when we have integrals, it gives us the exact area under the curve, but we are approximating the area under the curve here. So we have a couple ways to do this. We can do a left-hand estimate, a right-hand estimate, or a best estimate, right? Any one of these estimates will answer this question because it's very vague. On a quiz or on Wiley, it'll say which estimate it wants, but here it just says estimate. So when we do a left-hand estimate, I want you to notice here that my delta t equals 5, because here I'm counting by 5s down the table. So for a left-hand estimate, I'm going to do 5 times, for my first interval, I pick the rate on the left because I'm doing a left-hand estimate. So 5 times 42 plus 5 times. Now for my second interval, I pick the rate on the left, which is 51. I add that up and I get 465. Now for a right-hand estimate, I'm going to do the same thing, except I'm going to be picking the number on the right. So for the first interval, I pick the 51. And for the second interval, I pick the 60. Okay, I add those up and I get 555. Now, if I want to do a best estimate, I need to average those two numbers. And that gives me 510. So again, even though I see the integral, that is not what I'm going to be using as my tools to answer this problem. Okay. For example 3, again, we are going to be estimating. And again, I'm going to pay attention to the bounds, which happen to be at 1 and 3. So I'm going to mark those on my graph since they're not labeled. And I also know that I'm using n equals 1. So n equals 1 means I'm using one rectangle. So if I was going to do, let's do a right-hand estimate first. So if I'm going to do a right-hand estimate, I look at the 1 and the 3, I pick the value on the right, and that's going to give me the height of my rectangle. Because I want the right-hand corner to touch. Okay, so if I approximate that area, the width is 2, and the height is approximately 1. 2 times 1 gives me an area of 2. So that's my one rectangle that approximates the right-hand estimate. If I was going to do a left-hand estimate, then I pick the 1 to give me the height. And I see now that, again, I'm going to have a width of 2, but now I have a height of 2. And 2 times 2 is 4. So I have one rectangle for my left-hand estimate, one for my right-hand estimate, and then I can use those to answer my question, what are the bounds for the exact area under the curve? Well, I know that my area is bounded by my underestimate, which is 2, and my overestimate, which is 4. So the exact area under the curve would look like this. It's the area that we would find if we had the function. We could plug it in, but we don't, so we approximate again. Okay, so again, this is just to draw your attention to the fact that sometimes you will see a definite integral, but it doesn't mean you're plugging something in, especially if you don't have the function. If you don't have the function, you can't plug anything in. Okay, so be careful to read the setup, and sometimes you're going to be using the approximation techniques we had learned before. Okay, for example 4, this is just to help you, again, get used to plugging things in with a couple of just sort of the harder ones we do. So with part A, we're doing sine, but we need to make sure that we are in radians to get the right answer. For part B, I want you to practice putting in a power up here because sometimes that can be tricky with the parentheses. And then for part C, LNX, sometimes people have trouble finding that button. So I just want to make sure that you can carefully plug each of these in and just find an area under the curve. So I'm going to give you about a minute and a half to try to plug each one of these into your calculator, see what spits out. I'll tell you the answers that I got after, and you can compare, and then we'll look at some word problems that involve our definite integrals. Okay, so take about a minute and a half, and then we'll go through these. Okay, take about 30 more seconds. Okay, so as I mentioned, this is mostly a check to make sure that you can get the syntax right. Oftentimes, if you're not getting the right answer, it's because you've misplaced like a parenthesis or something small like that. So if you're not getting the same answers as me, I strongly encourage you to stop by Drop and Help sometime this week. And you can, share your calculator, or if you have something on a screen you're using, and me or the TAs can help you troubleshoot where the parentheses go, just to make sure you're getting the same results. Okay, so let's look at a couple word problems and look at how we might translate those and understand that we need to use a definite integral, as well as figuring out how we apply what we know. Okay, this one is split into 2 pages, so I'm gonna move this up and hopefully doesn't really balance, but we'll try. So example 5, it's important for pharmaceutical companies to test the characteristics of the drugs they design. The strength of a drug is given by R of M, where M measures the dosage, the amount of medicine absorbed in the blood. Suppose an experimental drug changes a patient's temperature at a rate of R of M equals 3m squared over m cubed plus 1 degrees per milligram of the drug. So that's the rate. Find the total change in temperature resulting from the first 4 milligrams of the drug. Okay, so I'm just going to write this function a little bit bigger, just because the print is really small. Okay, so I want you to think about how we might use that rate, what we might need to do, if we need to integrate, if so, what are the bounds that we need to use. So I'm going to give you about 2 minutes. See if you can work this out. See if you can figure out how to put it into your calculator, what the integral might look like if you set one up, having all the correct parts, and what the final result will be and what that result means. Okay, so take about 2 minutes and then we'll go through it together. Okay, take about 30 more seconds. All right. So this is the rate at which the temperature is changing per milligram. So if we want to figure out the total change in temperature, again, the word total is a key word that helps us know we're looking for area under the curve. We need to integrate this rate, and we're interested in the first 4 milligrams. So that means all the milligrams from 0 to 4. Okay, so it may only look like you're given 1 bound, but oftentimes if you're only given 1 bound, there's something in there that tells you can start at 0. So the first 4 means everything up to 4. And so we know that 0 makes sense as the initial because we don't have negative milligrams. And so if we're setting up an integral, we need our second bookend operator. Since the variable here is m, we would say dm. Now, when you plug this into your calculator, you will probably change those m's into x's, just because that's easier on the calculator to calculate. But when you plug that all in, you should get 4.17. So what does that mean? That means the change in temperature for the first 4 milligrams of the drug is 4.17 degrees, right? We're talking about degrees here. And so we don't know the temperature of the person, right? We can't say that their temperature is 4 degrees, 4.17 degrees. We say that their temperature changes by 4.17 degrees. Now, if we knew that their temperature was 100 degrees, we could say, okay, well, now it's 104.17, right? If we had an initial value to add it to, we could figure it out. But what this tells us is the change in the original function, not the value of the original function. So that's something we always have to keep in mind as we're computing this area under the curve. Okay, so let's look at another word problem example here. So the greenhouse effect is the rise in temperature that the Earth experiences because certain gases prevent heat from escaping the atmosphere. Just for clarification, the quotations around greenhouse effect are directly from the problem, not implemented by me. I believe in the greenhouse effect. I'm not really sure why it's in quotes. According to one study, the temperature is rising at a rate of 0.014 T to the 0.4 degrees Fahrenheit per year, where T is the number of years since 2000. Given that the average surface temperature of the Earth was 57.8 degrees Fahrenheit in 2000, we want to predict the temperature, the average surface temperature, in 2200, 2300, and 2400. So what is the impact of this greenhouse effect, right? We know the rate that's going to change our temperature. We know the current temperature, right? This is the current average surface temperature. And we also know that we are measuring since the year 2000. So we have to think about how we can set up an integral for each of these years we're trying to predict, how we will calculate the change in temperature, and how we would then relate the current temperature to make this type of prediction. Okay, so I'm going to give you about 2 minutes. See if you can set up some of these integrals, see if you can figure out how to take the information to answer the question, and then we will go through it together. Okay, take about 30 more seconds. All right. So what we need to do is we need to figure out our t-value for each of these predictions. So for this one, we're interested in what's happening from 2000 until 2200. So t equals 200. This is t equals 300. This is t equals 400. Okay. And then for each one, we're going to set up an integral for the number of years, so 200, and we're going to integrate the rate to figure out how much the temperature will change over that many years. Okay, so for A, we have 0 to 200. For B, we have 0 to 300. And for C, we have 0 to 400. So we're going to compute each of these definite integrals on their own to see what we get. So for the first one, we have 16.65. For the second one, we get 29.37. And for the third one, we get 43.94. So that gives us how much we expect the temperature to change over 200 years, over 300 years, over 400 years. But we're trying to predict the actual temperature. So this is where we need to then consider what the average temperature is in the year 2000, where we started our measurement. So for each of these, we're going to add the change. This is the change to the initial value. Okay, so the initial value is 57.8. And so our prediction for 2200 is going to be an average surface temperature of 74.45. In 2300, it'll give us a prediction of 87.17. And then in 2400, the average surface temperature will be 101.74. Okay. So this one's a little different because while we did use the definite integral to figure out the change, in order to answer the question, we had to use that change in conjunction with what we knew to be true as a starting value, which is sort of an extra step on top of what we've been doing so far. Okay, so sometimes in order to fully answer the question, you need to use other information, but hopefully you're starting to see that when we integrate the rate to get the total change of the original function, that's giving us important information to answer different questions. Now, something you may or may not have noticed, so you'll notice it here. I want you to see that every single integral that we've done so far has something in common. So I'll even put these up here, down here, in that whenever we take these integrals, we are getting positive outcomes, okay? And that is not always the case. So what we need to talk about next is how we determine whether or not an integral is going to be positive, what that means, what it means when it's not positive, and how that is all connected. And the way we talk about this is the relationship of the definite integral and area. Okay, so when you think about the word area, right, you probably think about things like, you know, rectangles, length times width, triangles, 1/2 base times height, right? Things like that, where area represents the amount of space a particular object takes up, right? That's our common definition of area. And so when we do this, and when we use this definition, area is always reported as a positive number. It wouldn't make sense for me to say that square has an area of -10, right? You'd be like, what does that mean, right? Are we in like a black hole of death? I don't know. So when we talk about area before calculus, the sort of agreed upon convention is that since area represents the amount of space we take up, it should always be positive, right? Because it's an amount of space and that space should be a positive value. However, I want you to think about what we are doing with the definite integral. Okay, so we're looking at some function, we are finding some area under the curve, and that is telling us how much the original function changes. Okay, if we only allow area to be positive, that means that our original function can only increase. It can only go up because we are always adding in that amount of area. And we know that that's not true. There's tons of functions that have derivatives that the original function decreases. It goes down for whatever reason, right? So we need to have this conversation about when is the area positive, when is it negative, and what does that mean? Okay, so when is f of x positive? So if your function is continuous and your function is positive, and so when I say positive, I mean above the x-axis, then each term that we're using to approximate the area under the curve and eventually get the exact area under the curve, so all these rectangles we've been sticking in here, okay, each of those is also going to be positive, right? These areas are going to be positive where the width, delta t or delta x, right, approaches 0, the rectangle fits more and more closely. And remember that the y value is also positive here in the way we're approximating. So think about the example of x squared. So we have x squared. If we're talking about, you know, a left-hand approximation, right? We start with something like this. This y value is positive, right? So whatever number this is, let's say this is, you know, 0, 1, 2, 3, right? This height, I'd plug a 3 into x squared and I get 9, right? So 9 times 1 gives me an area of 9. So every value I'm dealing with here is positive. So the area that I get when I do the integral is also positive. And that is because the function is above the x-axis, okay? So a typical example, like the one we've been looking at, the rate at which your income is changing is given by I of t equals 1.85 to the t in dollars per month, where time is in months. Find your change in income during the first year working, okay? If you were to graph this function, okay, let's show you what the graph looks like. Whoop, that's not what I meant to do. Go back. 1.85 to the x, right? That's my function. Let me move this up here. Right? If I were to graph this function, you will see that it is above the x-axis. So I would expect any area under the curve to be positive. Now, if setting up this integral at 1.85 to the x dx, one thing I have to be careful about here is even though I'm looking for my first year working, my rate is in dollars per month. So I have to turn my years into months in order for this to make sense. So the first year is actually 0 to 12 months, okay? Now, if I were to find the area under the curve, I can actually do this on a graph as well, if you'd like. If you go to second in calc, you can go down to number 7, which is going to give you the area. It asks for the lower limit. I'm going from 0 to 12, and it's going to shade in that area for me, okay? So this area above the x-axis is positive, which means my change is a positive change. This number that's at the bottom, in case you can't see it, is 26,1086. Okay, so my income has increased. Okay, this number is positive. My income has increased. My function is above the x-axis. Okay, but wait, what happens if we try to do this function, right? Everything we've looked at so far has been positive. So I'm going to go ahead and enter this one in here. So I have -1 to 1 of x squared minus 1 dx. And I get -1.3 repeating. Okay, so this is the first time we're seeing a negative value. And conceptually, this may be confusing to you at this point, because what does negative area mean, right? Like, how do we even visualize this? And so instead of trying to visualize what negative area would look like in terms of geometry, I want you to think really carefully about what we know in terms of relationships between the derivative and the original function. So I'm going to graph this function. So x squared minus 1. It's going to look like this. This is 1. This is -1. This is x. As a reminder, this is a rate, which is going to tell us something about the original function. If I were to think about the area between the function and the curve from -1 to 1, that is this area here. This area is below the x-axis. Okay, so that is different. All of the functions we've looked at so far have been exclusively above the x-axis. And that was intentional to get you to understand just sort of the basic approximation stuff. But now we are sort of expanding what we know. So I want to remind you that if the derivative of a function is negative, so if the derivative is below the x-axis, that tells us that the original function is decreasing. Okay. So if we get negative area, it's because the function is below the x-axis. And what that tells us is how much the original function decreases. Now, why would that make sense in terms of area? Okay. Now, if we just had this shape floating in space and we were in a geometry class, we would use sort of like arctangents or something like that to figure out the area, and we would report it as positive, right? But in calculus, where things lie have important meaning. So if you think back to how we approximated with our rectangles, let's draw in some rectangles here. Okay, remember the way we did the area was we did width, which was delta t, or delta x in this case, times the y value. The y value here, which represents the height of the rectangle, is negative, right? When your rectangles come down below, these y values that we're using to get the rectangle height, quote unquote, is going to be a negative y value. And that's different than what you do in most geometry classes, because in most geometry classes, you aren't mapping shapes onto a coordinate plane. So in this context, so in calculus, we can have negative area, and it makes sense because we are mapping onto the coordinate plane, and that negative area has a contextual meaning. And the meaning is that the original function is decreasing by some amount. Okay, so let's look at an example where we're going to look at a function that is going to give us a negative area and what that might mean in some sort of context. So, sorry, this should say January. So the average daily temperature from October 1st until January 1st is declining at a rate of negative 0.9 to the T degrees Fahrenheit per day. There are roughly 92 days between October 1st and January 1st. Determine the change in temperature over this time period. Okay, so I want you to take 2 minutes. I want you to sketch out what this integral will look like, the bounds, the variables you're going to use. I want you to find your area under the curve and then determine how you might talk about what that means. So what's a sentence that would describe what is happening based on the number you found? Okay, so take 2 minutes and then we'll look at it together. All right, take about 30 more seconds. Okay, so again, we want to integrate our rate to see what the total change will be. Since we're interested in the 92 days, our bounds are 0 to 92, and we see that the rate was in average temperature per day. So days matches up. This is how I entered this into my calculator just for syntax. Again, if you get an error, it's probably because you put a parenthesis in the wrong place. I do that all the time. But when we plug it in, we see that we get something negative. So we have negative 9.49. Okay, so negative 9.49. And remember that this number is telling us something about the original function, which is the temperature function. And so we know that the original function is declining or decreasing because of this negative. So what that tells us is that between October 1st and January 1st, the average daily temperature drops by 9.49 degrees. So I use the word drops to indicate the negative. We can also say, you know, declines, decreases, anything like that. So if we had the initial data, if we knew the average temperature on October 1st was 60 degrees, then we would do 60 minus 9.49 or 60 plus negative 9.49 so that we see that the temperature decreases during this time period. Okay, so negative area makes sense because here it represents a decrease in the original function. And so when we talk about negative area, we're talking about the position of the area on an axis, and that position is below the x-axis is when it's negative. Okay, So we're going to stop here. On Thursday, we're going to talk about what happens if you have positive and negative area, and also area between curves. Okay, so try out the homework on this before Thursday, and I will see you guys then.